In this video, we're going to discuss taking limits. It must be obvious that we don't want to look at a table and try to approximate every time a limit comes up. So it's time to look at some actual mathematical rules that we can use. So we'll just work through some rules and collect them together in a theorem. We're working with functions f of x and g of x. And these functions are defined on some common interval. And C is going to be in that interval. And we're going to discuss some limits as x approaches C. So we'll start with two rules that don't involve f or g. Rule 1, the limit of a constant function is that constant. Rule 2, the limit of the identity function x is gotten just by taking this limit and sticking it right in. We've made the observation that in general, you don't find limits by looking at what the function does at C itself. You look what happens near C, but the identity function is an exception to that. And we're going to see more exceptions down the line. These next rules will involve these functions. Let's say both of these functions have limits as x approaches z. Then the limit as x approaches c of the sum or difference of these functions is the sum or difference of these limits. A limit of a sum is the sum of the limits, in other words, and the limit of a difference is the difference of the limits. Now that we've talked about sums and differences, you might expect multiplication and division to come next. They will come, but let's look at a special case first. The limit as x approaches c of some constant k times the function function, we can pull constants out of limits, like so. Now the expected rule, we'll do an example with all of these rules later, which is why we are not doing any examples now. The limit of a product is the product of the limits. And we have a similar result for division, but this result with division has a hitch. There's an additional requirement. Usually, if you have the limit of a quotient, you can, let me be a little sloppy with my notation here for speed. You can break the limit of the quotient into the quotient of the limits, as you see. But there's an exception because these could be any real number, and potentially G could be 0, and you can't divide by 0, so you can only use this rule if this bottom limit isn't 0. It's sort of an unfortunate state of affairs. It's pretty fair to say this, I think, that taking limits is usually easy, but the limits we actually care about are trickier. So these rules work precisely when we don't need them and fail when we do. And a good example of that would be this sixth rule applied to this limit. You've seen this before. It's an average rate of change turning into an instantaneous rate of change. It's one of the most important definitions in calculus, and it's a fraction, but we can't use this rule because if we tried to use this rule, we would get a division by 0 error. So that is what it is. There's no use crying about it. We'll continue on with this. The limit of a power is the power of the limit. The textbook states this rule for natural numbers. I mean natural numbers in the power, it's true for other numbers, like for rational or irrational numbers. The eighth rule is really just the seventh rule, except instead of an n, we have a 1 divided by n as our power. We can take limits inside square roots, or any root, cubed root, third root, that is the cubed root, fourth root, whatever. If we're working on the natural numbers, sorry, geez, I keep misspeaking today. If we're working on the real numbers, which we usually are, this rule has restrictions on it. If n is even, this limit has to be non-negative in order to use this rule. In the next video, let's put all of these things together with a few examples.